Position, we've talked about change in time. Now we're going to talk about change in velocity. So change in velocity is your final velocity minus your initial velocity. We have the delta V, change in velocity. And there are 4 scenarios you can encounter with acceleration or changing in velocity. And the first couple are really straightforward because they're things that you can kind of wrap your head around. The last 2 get really confusing because the sign direction thing gets really mixed up. So let's maybe just look at them and then we'll see how we do. This is a drag race car. Describe the change in velocity. If you've ever seen a car race before, this is like a straight down the drag strip type of race. What's happening to the car's change in velocity? What velocity is it starting with? What velocity is it ending with at the end of the race? How would you describe the change in velocity? Another way to think about it is it speeding up? Is it slowing down? It's another good way to describe a change in velocity. Anyone want to describe the change in velocity? Anybody ever been to a drag race? You know that the cars start at a stoplight type thing. So they start at 0 velocity, they're not moving, and then they speed up very quickly, so they're increasing their velocity. So the change in velocity would be from 0 to something big. Now, if we think about change in velocity as the final minus the initial, the change in velocity is going to be really big. We don't want to talk about how fast, because you're implying a time there. I'm going to have to sneeze here. Trying to keep it off. Can I do it? Okay, I think I can do it. So don't think about it in terms of how fast. We're not talking about time at all here. We're talking about its velocity, how fast it's moving. We will eventually talk about how long it took, but not yet. So change of velocity. If I have a dragster, it starts at 0, it ends at, let's say, 300 kilometers per hour. That's how fast it crosses the finish line at. So what was this change? It went from 0 to 300. So if I take the final speed at the finish line, 300, and I subtract 0, its change was 300. It went from 0 to 300 kilometers per hour. Okay? How about this? Space shuttle. Well, they don't fly anymore, sadly. If it lands, what's its change in velocity going to be? How is it different than the drag car? Is it different at all? Are they the same change in velocity? Are they different changes in velocity? What is one of the fundamental differences between these 2 examples? So drag race car starts at 0, speeds up, goes really, really fast, and finishes the race. The space shuttle lands, and when it touches down, if you've ever been on an airplane before, same sort of thing, touches down, it's going really, really fast, and then you can see all these like speed brakes get popped out and big parachute out the back to slow it down. It would eventually stop. That's the point of landing the spaceship. If you can't stop the spaceship, well, you can't get out unless you want to just jump out of a moving space shuttle, but that's probably not a good idea. So I feel like you guys are looking for really complicated answers to really simple questions. It will have a slower velocity that goes closer to 0 on a graph. Not talking about a velocity compared to one another, not talking about graphs, just what's happening to the change in velocity. Let's say the space shuttle flying lands on the runway, it's going 500 kilometers per hour. Super, super fast. Throws that parachute out the back, the parachute slows it down, the air brakes deploy, eventually the space shuttle is going to come to a stop. So what is its change in velocity going to be? How fast was it going? Let's say it started touchdown at 500 and then stops. Its final velocity is what? Well, it stopped, so its final velocity was 0. What was its initial velocity? Well, I just made up 500. It's way too big, but we'll just pretend. 500. So 0 minus 500 is negative 500. The velocity changed by 500. It actually slowed down by 500 instead of sped up by 500. Sure, let's do these and then maybe we'll have some epiphanies or something. All right, how can you tell from a distance versus time graph whether a motion involves acceleration? We haven't even talked about acceleration, so we're just going to skip you for now. Question 1. Yeah, I don't want to do any of these. I've changed my mind. Don't want that, I want that. Let's just look at examples 3 and 4 here. If a car is driving along at 100 kilometers per hour, is it accelerating? We haven't even talked about acceleration yet. So let's just skip that. Acceleration. Let's talk about the definitions and then we'll go back to look at those questions. Now, before Ava, you said, is it how fast the car takes to get to its top speed? And that was kind of what we're getting to right now. So acceleration is the rate of change in velocity. It's how fast you change your velocity. So two objects with the same change in velocity can have different accelerations, which is kind of confusing, but we'll talk about that in a second. Let's think about these two cars, kind of like the drag race car we started with. Suppose these vehicles starting from rest speed up to 60 kilometers per hour. They'll have the same change in velocity. Which one of these cars is going to speed up faster? The super cool drag race car or the old-fashioned car? They can both get to 60, but which one's going to get there faster? And which one will have a greater acceleration? Is anyone out there today? I don't mind showing up to teach you guys, but if you're just going to sit there, then we're not going to really get anywhere. The race car. Thank you, ladies. Of course, the race car is going to get there faster. Now, if we talk about change in velocity, they're both starting from rest, or 0 velocity, and they're both finishing at 60 kilometers per hour. So just talking about their change in velocity isn't enough to describe the acceleration. Now, the race car is going to get there a lot faster than the old car. So what does that mean? Well, we talk about the acceleration being the rate of change in velocity. So because the race car is getting to 60 kilometers per hour a lot faster, it's going to have a bigger acceleration. Whereas the old car, it's going to the same speed, but it's going to take longer. So it's going to have a lower acceleration. So that's a really great way to kind of think about what acceleration is. Now, if you've ever been in a car, bus, plane, when you're at a stoplight in a car, you step on the gas, you kind of get pushed back into your seat a little bit. That's what acceleration feels like. Same thing, if you're cruising in your car, you hammer on the brakes or your parents hit the brakes, and all of a sudden you go forward really, you feel yourself wanting to move forward, but the car is kind of slowing down behind you sort of thing. So that's what acceleration feels like. You can have acceleration forward from a stop line, or you can have a negative acceleration, it means you're slowing down. So velocity versus time graph acceleration will be shown by the slope being positive. Yes, that is correct. All right, so from a distance time graph, how can we describe acceleration? I still don't like that question. Let's look at examples 3 and 4 here. Example 3. Car is moving along at 100 kilometers per hour. Is it accelerating? You're traveling to Vancouver, 100 kilometers per hour down the connector. Are you speeding up? Are you slowing down? No. So a car that's traveling in a straight line at 100 kilometers per hour is not accelerating. It's not speeding up. It's not slowing down. You haven't put your foot on the accelerator. You haven't hit your foot on the brake. Those two things would make you either speed up or slow down. Number 4 is a really kind of profound question in physics, which a lot of really amazing things come out of, but we kind of don't talk about that till physics 11. But imagine you were on an airplane and you had earplugs in and you had a blindfold on and you're just sitting on a plane. Would you know that you were moving if you were on a plane with a blindfold on and earplugs in? You maybe don't know how you got onto the plane, but could you tell you were moving? Or if you were in, think about like a really big bus or like a motor home traveling down the highway, blindfold on, earplugs in. You can't see, you can't hear. Can you tell if you're moving or not? What do you think? And I'm not looking for like really small details like every time you'd go over a bump, you'd feel it. Or like turbulence in an airplane, nothing like that. Feel it, yeah. No, unless there's turbulence, yeah. Perfect. So yeah, you have no way of telling, and maybe even like an elevator. If the elevator is going up or down, can you tell? You can't see out, you're completely enclosed. Could the elevator be going up when you want it to go down? Sure. You have no way of knowing until something happens. So if you're on the airplane, earplugs in, blindfold on, you wouldn't be able to tell until the airplane landed and started to slow down. Or if you're in a car or a bus, if the person were to speed up, you'd feel like you're going backwards. If the person slows down, you'd go forwards. So this is what acceleration is. I can be traveling in a car or a plane going 300 kilometers per hour and I don't feel it. It doesn't feel any different. But as soon as the plane speeds up or slows down, I can feel that. So that's what acceleration is. And then the faster the acceleration happens, the more you can feel it. The last 3 sets of formulas we have are acceleration is change in velocity over change in time. And we describe this as the rate of change of velocity. So if I go to your data booklet on the bottom, you can see that we have these formulas for acceleration. Acceleration, change in velocity over time. If you want to solve for velocity, it's acceleration times time. And if you want to find time, it's velocity divided by acceleration. And then you have the 3 change in velocity formulas. This one's isolated for change in velocity, initial velocity, final velocity. So these are your physics formulas. This is all you'll need for chapters 8 and 9. All right, so we have a pool ball. And it's traveling at 2.5 meters per second towards the cushion, and the cushion is just the edge of the pool table here. It bounces off at 1.5 meters per second. So the ball comes in, hits the edge, and then bounces back. What was the ball's acceleration? So pool ball cruising along, boing, bounces off, goes back the other way. Yeah, if you were to live in the United States, you'd be doing all your questions in feet per second, which is a common unit there. We're not in the United States, so we do ours like the rest of the world in meters per second. All right, let's do this question. There's some really kind of weird things that come as a result of this. First thing, we need to pick a direction. Do we want right to be positive which is your different than mine, or do we want left to be positive? Well, normally we say everything going to the right is positive. So I look at my diagram, I see that this guy is going to the right, so I'm going to call this a positive direction, and then this guy is going to the left, so I will call this a negative direction. Very important we get that out of the way to start. All right. What is the ball's acceleration? The question is asking us to find the acceleration, which is a change in velocity divided by a change in time. Remember the arrows on top of these things just mean these are vectors. I could just get rid of them altogether and the question would be the same. Remember the change in velocity. Off the back of our data booklet, change in velocity is final velocity minus the initial velocity. That is a change in anything. A change in time is the final minus the initial. A change in pressure is the final minus the initial. Doesn't matter what the example is. So in this case, we need to find out what the final velocity is, and we need to figure out what the initial velocity is. Now, the reason I made these kind of sign things really important in the beginning is that my signs are different. My ball was moving to the right, hits the cushion, then it bounces off to the left. We can call it acceleration or negative acceleration, deceleration, or negative acceleration. I will try to stick with negative acceleration, but deceleration works as well. So my final velocity is negative 1.5 meters per second, and my initial velocity was 2.5 meters per second. Hopefully that makes sense. I need to differentiate between the direction these things are traveling. So if I want to find the change in velocity, I need to take the final, which I'm calling negative 1.5, and I'm going to subtract the initial, which is 2.5. So negative 1.5 minus 2.5 is negative 4 meters per second. Now this is what you guys were asking before. Do I need to say it's to the left? Well, not really. The negative sign here tells me it's to the left. I've decided everything in my question to the right is positive, so if I have a negative, then I know it's to the left. So I want to find the acceleration. That's what the question's asking me to find. In order to find the acceleration, I needed to know what the change in velocity was, which I just found out was negative 4. This gets back to the idea of the old car and the new car accelerating. Well, they both got to 60, but the drag racing car got there a lot faster, so it had a greater acceleration. Now, in the question, it tells me the time it took was 0.2 seconds. So if I wanted to find the acceleration, I'd go 40 divided by 0.2, which is going to be the same thing as 40 times 2. Negative 4 divided by 0.2. I'm a step ahead of myself here. 4 divided by 0.2 is going to give me 20 meters per second, which is kind of a really goofy unit, meters per second. What we end up doing is calling this meters per second squared. If you want to think about this, might help you a little bit. If you think about negative 20 meters per second is how fast it's changing. So 20 meters per second is a velocity. And we talk about acceleration being the rate of change in velocity. So it's how fast the object changes its velocity in a given amount of time. So what this means is negative 20 meters per second means that every second the object's changing its velocity by 20 meters per second. We also call that 20 meters per second squared, and those are the units we'll always use But if it makes more sense to think about it as 20 meters per second every second, then go with that. So it's changing its velocity by 20 meters per second every second. That is the acceleration of this pool ball. Let's look at a few more. All right, the next question says a car accelerates from rest to 3 meters per second for 5 seconds. What's the velocity of the car at the end of 5 seconds? All right. If it accelerates from rest, this is a really important piece of information. That means your initial velocity is 0 meters per second. The other piece of information I'm given is, this should say 3.0 meters per second squared, but the superscript didn't work. So that's your acceleration. And then this guy here is a time. So I already have the formula. Change of velocity is the acceleration times the time. I know my acceleration is 3. I know my time is 5. So my change in velocity is going to be my acceleration, 3.0 meters per second squared, times a time of 5.0 seconds. So my change in velocity is going to be 3 meters per second squared. So every second, I'm changing my velocity by 3, and I'm doing that for 5 seconds. So the first second, I've changed it by 3. The second section, I'm up to 6. The third second, I'm up to 9. If I kept doing that for 5 seconds, I would end up at 15 meters per second. So if I started at 0, each second I increased my velocity by 3. I did that for 5 seconds. If you just think about it in your head, you start at 0, 3, 6, 9, 12, 15. 5 seconds later, you're at 15. If you do the actual calculation using the formula, you're going to end up with the same thing. Now, I don't have a direction, so I just leave it as positive 15 meters per second. My change in velocity is going to be 15. Now we found a velocity, and velocity's units are all going to be in meters per second. What we're doing here, if you think about the math, is you have meters per second squared, and then you're multiplying it by seconds on the top. And remember, this is like seconds to the power of 1, and then you have seconds to the power of 2 on the bottom cancel. So kind of getting back to your exponent laws, you're going to end up with meters per second, not meters per second cubed, because those seconds are on the top. All right, what else do we have? Acceleration is the rate of change in velocity divided by time. An example of acceleration might be 10 meters per second each second, or 10 meters per second squared. All right, let's look at another example. A truck started from rest. As soon as I see from rest, that means my initial velocity is 0 meters per second. And it sped up at 10 meters per second every second for 5 seconds. How fast would it be going after each second? Okay, here's my truck. I have 0 seconds, I have 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. All right, so my truck is accelerating. It started at 0, and then it sped up to some speed. I want to figure out the velocity at each of these times. Okay, if my car is accelerating at 10 meters per second, every second, how fast would my car, or truck I guess, be going after 1 second? Started at 0, increasing it by 10 every second. How fast am I going now? I'm going 10 meters per second. All right, what about a second later? I started at 0, now I'm going 10. Every second I'm increasing my speed by another 10. So at 2 seconds, how fast am I going? I'd be going 20. I continue to accelerate 10 meters per second squared, or 10 meters per second every second. I would eventually end up at 5 seconds traveling at 50 meters per second. So each second, the truck is increasing its velocity by 10 meters per second. That's what 10 meters per second means, or 10 meters per second squared. Okay, we can do this. Maybe I'll do one of these. We'll talk about the scenarios. Let's just talk about the scenarios. Got about 5 minutes or so left. All right. Describing acceleration. I'll come back and do some of these next day. Positive and negative acceleration. This is why acceleration can get a bit tricky, is because your acceleration can be negative sometimes. What does that mean? So if you're in a car and you're speeding up in the forward direction, this is kind of like you're at a stoplight, the light goes green, you increase your velocity. You put your foot on the accelerator, which is called an accelerator because it accelerates your car. If my velocity was going forward and my acceleration was going forward, would my car be speeding up or would my car be slowing down? What do we think? Speeding up, slowing down. The first two examples are very straightforward, and then they get trickier. For all of those of you who said speeding up, you are correct. So your car is moving forward, you're accelerating forward, your car is going to speed up. Is it possible to accelerate backwards while your car is going forwards? Yeah, that's what happens when you're driving in your car and you put your foot on the brake. You come to a red light. Your velocity is forward, your acceleration is actually backwards because you're slowing down. So this is why acceleration gets tricky, because it's kind of hard to wrap your head around that. You're moving forward, but you're changing your velocity negatively. You're slowing down. Your final velocity is going to be 0, but your initial velocity was 50 kilometers per hour. So your change in velocity is actually negative. We'll talk about graphs later. We don't want to confuse ourselves right now. So your change in velocity, because it's negative, you're going final velocity, which is 0, minus your initial, which was whatever, 50 or however fast you were traveling. Your velocity is still going forward, but your acceleration's backwards. Weird. Two other scenarios. These ones are a little bit more complicated. Now, This is kind of like the first scenario, except everything's backwards. If you're in a car, you're in reverse. You're speeding up going backwards. Has that ever happened? Sure. You drive into your garage, park your car, wake up the next morning, time to go to school. Jump in your car, put it in reverse, put your foot on the gas or the accelerator, and you start to speed up going backwards. Your velocity is backwards. Your acceleration is backwards as well. You started at 0, you started at a stop, and you increased your velocity going backwards. So both your velocity is negative and your change in velocity is negative, so your acceleration is negative. The last one is the complicated one. Let's imagine you were going backwards and you wanted to, eventually stop and go forwards. You just didn't want to drive backwards all the way to work. So you're going backwards, you put your foot on the brake and you start to slow down going backwards. Means that your velocity is backwards, but now you're accelerating forwards, which is kind of hard to comprehend. So I'm going to go back again. Now you know what to expect. You're stopped at a stoplight, you put your foot on the gas, you accelerate once it turns green. Your velocity is forward, your acceleration's forward, they're both in the same direction. Easy peasy. The next one's kind of straightforward as well. You're moving forward, the light turns red, you slow down, so you have a negative acceleration, and then you come to a stop. Your velocity and acceleration are in different directions, you're just slowing down at a stoplight. That one makes sense. How about this one? You're moving backwards and you're speeding up going backwards. That makes sense too? Maybe. The fourth scenario is you're going backwards, but now you're slowing down going backwards. So your velocity is backwards, your velocity is negative, but your acceleration's forward or positive. So those are the 4 scenarios you can encounter. All right, I'm going to leave you guys there. Let's just take a look at the learning guide for Unit 9. You guys will be obviously trying to finish off Unit 8, get that learning guide in. You had a few questions there to do, so I won't spend a ton of time looking at this, but assuming you can get Unit 8 in the next couple days, you should have Unit 8 test written by the end of the week for sure, by Friday. This is what Unit 9 looks like. So we should be able to do the first page. Let's just keep it simple. So if you want to stay on top of things, first page Unit 9 learning guide would be great, but obviously worry about Unit 8, getting that finished and the test written. I will begin next day's class with answers to any questions you might have had on the Unit 8 learning guide now that we've finished that up. So you should have Unit 8 learning guide polished off tonight or tomorrow. And then if you had a few questions, we'll go over them in class on Wednesday. We'll continue on with Unit 9. I hope if you guys don't have a ton of questions, we'll actually finish off Unit 9 on Wednesday, which really means we're finishing off the course, which is kind of crazy. If we have to drag it on into the following week, then that's okay. One other thing I wanted to mention is on, not this week on Wednesday, but the following week on Wednesday, I've got a lab at KSS for us, reserved, and we can go there and actually do a lab activity, which would be really fun. Get to use some really cool like handheld graphing type things, and they're called LabQuest units, so it'll be great. So if you guys want to come to that, we'll be doing that on the 8th, and I'll talk a bit about more about that next day. So I'm going to leave you there. Finish Unit 8. That's priority number 1. I'll answer questions next day on anything you had on Unit 8. We'll keep going on Unit 9 next day. I hope to finish. There's not a lot left. So we'll finish Unit 9 next day, and then we'll start reviewing from there. So have a great afternoon, and we will see you guys on Wednesday.